Okay, everybody, welcome. So today we're going to be discussing the types of bonds and their characteristics. So first off, we have to talk about why things bond, okay? And the reason things bond is that systems with less energy are actually more stable in nature, okay? And so being bonded actually requires less energy than atoms being in their elemental form, okay? Especially for things like the alkali metals, okay? For the most part, elements really need to be in a compound to be stable. The noble gases, of course, are an exception to that, as are a lot of metals. But for the most part, elements really need to be bonded in order to have the least amount of energy and be the most stable in nature. So the thing is that energy is released when bonds form, okay? Because the elements are actually decreasing the amount of energy that they have. That's why they're bonding in the first place. So once they bond, energy is released. Energy is absorbed in order to break a bond. So it requires energy. Energy is necessary in order to break a bond. So when we form bonds, that is actually exothermic. Energy is released. It is given off to the surroundings. And breaking bonds is endothermic because it requires the addition of energy, okay? And that should be kind of a review of stuff we talked about in Chem 1. Okay, so the next thing, let's talk about what a chemical bond is, okay? So chemical bonds are forces of attraction that hold groups of atoms together and allow them to function as one single unit, okay? So it no longer acts like the element. Instead, it is part of a unit, and that unit functions as a separate thing than the elements that make it up. So sodium is superreactive and it's a metal. Chlorine is a superreactive nonmetal and it's a diatomic. But once those two elements combine and they form sodium chloride, all of a sudden they're a pretty boring salt, right? Okay. The type of bond that forms between atoms is related to the physical properties of the substance. So the different bonding types give those substances different physical properties. And this goes back to the electronegativity of the elements, okay? Often called electron affinity, right? The ability to hold on to electrons or attract electrons. The difference in that electronegativity between elements actually can determine the type of bond that forms between them, okay? And also, just a kind of a note here, the greater that difference in electronegativity, which is going to be delta En, the more polar that bond is said to be. In fact, sometimes it can be so polar that it can be ionic. So that's where we're going to start now. Ionic bonds have the greatest difference in electronegativity. So the electronegativity difference in an ionic bond is going to be greater than 1.67, okay? Electrons are transferred from the cation, which is positive, to the anion, which is negative, okay? They contain a metal, usually, and nonmetals, okay? There is a strong, what we call electrostatic, and so that's kind of like a magnetic attraction between your positive and negative ions. So between those cations and anions. It's that electrostatic, aka magnetic attraction, that kind of holds these things together. The formulas for ionic compounds are written as a ratio of elements, and so that's going to be an empirical formula. Okay? They are solids at room temperature. They are crystalline solids, which means that they have a crystal lattice structure. And so there's a picture of this in the book, but basically what happens is you get this three-dimensional crystalline solid where you have positives and negatives kind of alternating, or they may be in a ratio, and it sort of forms this three-dimensional shape with positive and negative alternating charges. I'm not an artist here, but, and then this one should be negative. If that one's positive, this one should be negative. That's positive, negative. Anyway, you get the point. You get this three-dimensional structure where positives and negatives are kind of alternating. And so that forms the crystal lattice structure. And again, there's a way better picture of that in the book. Okay. Ionic compounds, because they have that strong attraction between positive and negative, have very high melting points. It is high to melt these ions and separate them from each other. And because we have the movement of electrons, we have a difference in charge of positive and negative. When these dissociate and dissolve in water, they will conduct electricity, which means that they are electrolytes. Okay, so that's a definition of an electrolyte. It is a substance that when dissolved in water will conduct electricity, and your ionic compounds are going to be the ones to do that. Okay, so then another type of bonding is known as metallic bonding. And this is the specific bond between just metal atoms. Okay, so there is what we call a sea of delocalized electrons surrounding the positively charged nuclei of metal ions. So the way that it works is you would have a metal, let's say iron, and it would be positive. All of its valence electrons would kind of come off of there, and those electrons would just kind of be swimming around all the atoms. Okay, so they're not specific to one, like this iron atom doesn't have its valence electrons surrounding it. Instead, all of the valence electrons kind of delocalize, aka they just kind of come off of there, and they form this sea, right? It's just kind of this area of electrons. And so these nuclei are just kind of hanging out in all these electrons floating around them. There's an attraction between those metal ions and the delocalized electrons. And so it's that attraction that actually holds everything together in the bond. Formulas are written not like a compound, okay? They're written as neutral metal symbols. So for example, this would just be Fe. Okay, they're solids at room temperature. Again, they're crystalline solids. Okay, so you would have points where these atoms would be, and then they'd be kind of having the electrons going around them. Okay, they are malleable. They are ductile. They are good conductors of heat and electricity. And all of that is due to the nature of this electron structure here, that it's just kind of all the electrons are all over the place. They're able to move between atoms. And so that gives that sort of ability to move, right? And so that allows them to be bent into shapes and pulled into wires. And it also allows electricity to flow through this sea of electrons, again, because we have a separation of positive and negative charge. And so electricity and heat are both able to move through this metallic structure. And then last but not least, we have covalent bonding, okay? So in covalent bonding, the electronegativity difference is always less than 1.67. If it is a non-polar covalent bond, then the electronegativity difference is extremely small. It is less than 0.4. If it's a polar covalent, so slightly more polar, right, slightly more towards ionic, then it's going to be greater than 0.4 but less than 1.67. Okay, if you go past 1.67, it becomes ionic. Okay, this is a bond between nonmetals. Electrons are being shared between atoms. If they are nonpolar covalent, then those electrons are being shared equally. The electrons are laying right between the two atoms. If it's polar covalent, it's not fair sharing. The electrons will be closer to one atom than the other. They'll be closer to the more electronegative atom. Okay? Formulas are written as the true ratio of atoms. So these are going to be molecular formulas. Okay? Covalent compounds exist in all states of matter. So some are solids, some are liquids, lots are gases. They have pretty low melting points, and they are non-conductors. They do not conduct electricity. Okay, that's because there is no movement of electrons, there is no separation of charge, there are no charges at all. You have electrons situated between atoms being shared, and so that prevents any movement of energy. It also makes these substances, if they're solid, brittle, and lots of them do exist in the liquid or gaseous form, and we'll talk more about that in another class. All right.